Welcome to the course Introduction to Algorithm. My name is Saurabh Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. In this lecture, we will cover balanced binary search tree or balanced BST. So, this is lecture number 9. So, in this lecture, we will mainly start with the what do we mean by binary search tree. Then we will see a binary search tree how can be used for a sorting algorithm, that is binary search tree sort. Then we compare binary search tree with the quick binary search tree sort with quick sort. From there we will see that both the time complexity are same. So, from there we can get the expected height of a randomly built binary search tree, and then we will see that is the balance. Expected height of a randomly built binary search tree is balance, but that is expected, but we want to get a guaranteed height balance binary search tree. So, there we will talk about red black tree, which is a balanced binary search tree, and we will discuss some properties of the red black tree, and we will discuss how we can, that is a dynamic set, how we can insert a node in the red black tree. So, these things will be covered in this lecture. So, let us start the lecture. So, let us start with the what is a binary search tree. So, it is a binary tree rooted by a rooted binary tree, and we have a root node, and then each node, binary tree means each node is having maximum two child. It could be 1, it could be 0, leaves are no child. So, that is the binary tree. Each node can have maximum 2 child. Now, internal node, I mean each node, what each node is storing? Each node is storing a k or key. So, this key can be associated with a record. So, we have seen that each record is having a field which is called key field, and that key field we can store the record based on this key field. So, this node is actually will be storing the key field of a corresponding record. Now, each node have 2 subtree, one is left subtree, right subtree, but lib node has no subtree because lib node has no child. Each node can have at most 2 child. Okay. So, now the property, this is an example of this is a binary tree, okay, and this is an example of binary search tree. So, what do you mean by search tree? So, search property is if we consider any node. So, we will come to that property. If we consider say this node, now this is the left subtree, this is the root node, and this is the left subtree root, and this is the right subtree, this one. So, this is the left subtree, this is the right subtree. Now, if we consider any node in the left subtree, that key value of that node must be less than this node. If we consider any value, any node in this right subtree, if you consider key value, then that value must be greater than this node, and this property must be true for every node, not only the root. Say for example, if we consider 3, now 3 is a node. Now, we consider the left subtree of 3, this is 1, and this is the right subtree of 3. Now, if you consider a node in here, any node, that must be true for every node. Any node in the right subtree of this 3, the key value is greater than 3, and here key value is less than C. So, that is that tree is called binary search tree, that is called binary search tree. So, this property must satisfy. We consider a node in this tree. So, this is our tree, say we consider any node at any point of time, any position. So, this is the left subtree, and this is a right subtree, sorry. So, if this value is x, then every node over here the key value must be, if x is the key value, less than x or less than equal to if there are equal element, and this must be greater than x. So, this is the property of binary, and this must true for every node including the root, leaves, every node. So, that is the property of binary search tree. So, this we can just, so this is a binary search tree with size 9, there are 9 nodes and the depth is 3. Okay. So, the height is 3 basically. Now, this is the property which we have discussed. So, consider a node x at any position of the tree, then consider the left subtree of x and consider the right subtree of x. Now, if y is a node in the left subtree, then the key value of y must be less than key value of x. And similarly, all the nodes which are in the right subtree of the x are greater than the key value. Key value must be greater than equal. If there are some equal elements, we have to use the equality. Otherwise, if they are all distinct, we can say strictly. Okay, so this is the property of binary search tree. Now, what are the operations we can think on binary search tree? We must able to insert. This is a dynamic data structure. We can able to insert a element in the tree. So we can. So this is kind of, we are storing some record in a tree structure. Okay, so that when we search it, it will be faster way. I mean, that's why we are looking for balanced, so that height will be the search time. We will see that. And since it is a dynamic set, this data structure is for dynamic set of collection of records. So deletion also should be a one operation there. So we should able to insert a new node, we should able to delete a node, and then the search, we should able to search a node, we should able to search a record whose key value is given. So that is called lookup or searching. So this search should be in a faster way. We will see how search can be done in a binary search tree, and then we will see how the height is important. So search, worst case search is basically the height of the tree. So if the height is n, then we have to go for log n. So that's why we are looking for balanced binary search tree. Okay, now let us just discuss the binary search tree sort, how we can use a binary search tree to have a sorting algorithm. Okay, so for sorting algorithm, what we have? We have given an array of size n. We need to sort it. We have given the n element which are given in the array. Say this is the input. So a1, a2, a1, a2 up to an. So this is the input. There are n elements given in the array. Say a array, which we need to be sorted. So this is the input of any sorting algorithm has an input of n element to be sorted. Okay. So now what we do? We first create a binary search. We will use the binary search tree for this. This is called binary search tree sort or BST sort. So initially T is empty. Nobody was there. Now we create a empty tree. Basically, we have to create a pointer, because this is tree implementation of tree means we should have a pointer. So this is the top of the tree, you can say, I mean root pointer or something like that. Now we have to insert the node, insert each of this node in the tree. Okay, so that is the tree insert, BST insert. So we will see how the insert will be done. So we will see by an example, and then after this tree is formed, this is the tree is build BST by this. So this is, we are inserting each node, each element as a node of the tree by doing the tree insert. So that we will see by an example how the tree insert will be done. And then after that, once the tree is formed, this tree is formed, then we perform the in-order tree walk to get the sorted one. In-order tree walk, if we do, we will see what is in-order tree walk, then it will give us a sorting order, sorted elements of these elements. So let us take this example. Suppose we have given this numbers to be sorted. So 3, 1, 8, 2, 6, 7, 5. So this is given in a array. Now we have to first create a tree with a root. So root will be the first node. So we first start with the root, that is the 3, first node, and then this is for I is equal to 1, that is the root, and then we insert. So this tree insert means we will check whether this is empty or not. If this is null, we just insert, otherwise we will do the again the searching. Searching means until we get a null node there, empty node. So now next element is 1. So we check with the root. Now 1 is less than 3, so we have to go to the left part of the tree. And left part there is nobody, it is null, empty, so we insert 1 over there. We can do this in a recursive call also. Okay. So we insert 1 over there. Now we again put this left child, right side child as a null or empty. Then we go for the I is equal to 3. So that is the this is the A3 or 8 we have to insert. Now we start with the root. 3 is greater than 8 is greater than 3, we have to go this part. Now this is null, so we can insert 8 over there. So insert 8. Now we have 2, we start with the root, and 2 is less than 3. So this is the tree, we have to again call this tree insert on this subtree. This is a recursive call, you can say. So now 2 is greater than this new root, so 2 has to go to the right. So 2 we have to insert into the right. Then 6. So 6 is greater than 3, we go right. Then we compare with this new root, that is a recursive call. Again you can say tree insert call. You can write the pseudo code for tree insert, that is not a big code. So now we compare with this. Now 6 is less than 8, so 6 will be inserted here because this is null, nobody is there. So we insert 6 in the left of 8. Now again 7, so 7 will be greater than, 7 is less than 8, so 7 is greater than 6, 7 will be inserted here. Now we have last node which is 5. So we start with here, 5 is greater than, so we come to this tree, this root, new root. So we compare with 5, we come to this tree, now this root, and then we compare, this will be inserted here because this has to go to the left. That is the way we create a binary search tree. So this is the tree insert. We insert a node in the tree by this way. So that is the build BST, you can say, build binary search tree. So done. So this is our binary search tree created by this. So this is this code. Up to this we form this. Okay. Now we perform in-order tree walk. What is the in-order tree walk? In-order tree walk is nothing but first we start, we call with the root node, then we first print. It is how we explore all the node in the tree in order to if we that is the walking. So there are 3 types of printing process we can do: in order, pre-order, post-order. So in order means we first print the left, we first explore the left, then the root, then the right recursively. So if we do that, we first explore so we start with this root 3. So 3 before that we must explore all the nodes which are here in the left part, and we know all are less than 3. So that there again we call recursively, this is the new root. So again we print all the nodes which are left, nobody. So we print then 1 and then we print 2. So we print 1, then 2, and then root. So this exhaust, then root 3, then we go to the right part. So left, root, right. So that is the ordering we should print the nodes. So in the right part again 8. So we first print the left part, then in the left part we print, we go to this 5, 6, 7, then 8, and done. So that is the that is the sorted one on this. So that will take this in-order tree walk will take linear time because each time we are printing one element. So there are n elements, it is linear time. But how much time it will take to build BST? So that we have to see. So that will depend on the input, or that will depend on the tree structure. So if the tree is like this, when will be tree is like this? We will see some example. So now let us discuss the time complexity for BST sort, which will fully depend on the build BST. So the time to build BST is basically a summation of the depth of x, where x is in the tree. So basically if we have a node x, so if this is the tree, Suppose we have a tree like this and we have a node over here which is x, and we have, this is our tree. Now this is the root. So this is the, so depth of x means we have compare x this many times, that is why we have inserted here. So that means whatever the depth of x for each x, that many comparison we are doing. So this is basically to insert x, we had to do that many comparison. For root there is no comparison, and for the next node we had to compare with root. So that is, then we insert, so that is the depth of that node, and next node depending on where it will go. So we have to compare. So it will go to the depth, it will go to that node, and the depth is the number of comparison basically. So the depth, so it is basically summation of the depth, and this T is our tree, the BST. So that is the time to build BST. Now depth means depth will depend on the type of the input. So we will take some sorted one. So if the input is say 2, 4, 5, 7, 13, then what will be the BST? So 2 is the root. Sorry, this we should erase. Yeah, so 2 is the root. So 2 is the root, then we insert 4, then 5, then 7, then 13. So this is the tree, and this is the like this. Okay. And what is the depth of each node? This is 1, this is 2, this is 3, because this 3 times we compare. So what is the sum of the depth? This compared, I mean 2 times, this compared 3 times. So basically time complexity is the 1 plus 2 plus 3 up to n order of. So that is basically n into n plus 1 by 2 arithmetic series. So that is order of n square algorithm, because this tree is not a good tree. It is just, even this is true for if we have a reverse sorted array, then also it will be like this, and then also sum of the depth is basically that 1 plus, because 1 plus 2 plus that will be give us order of n square time algorithm. Okay. So the time complexity of this is order of n square. This is order of n square algorithm for doing this. Okay. So now let us talk about when we have a better option, when the tree is, this is not a good tree, this is not a good tree, this is a bad tree. So then what is a good tree? Good tree is like this. This is, I love to draw this tree. Yeah, this is a good tree, because this is, if there are n nodes, what is the height of this tree? Height of this tree is log n. And then in this case, what is this time? What is the sum of the depth? Sum of the depth will be L log n, because that is the because there are how many nodes are there in the leaf node? N by 2 nodes are there in the leaf nodes. So for those n by 2, we need to go down to the this height. So that is log n. So that is order of L log n. That is the time complexity for build the tree, and that will be the time complexity for BST sort, because that is the major time, because in order tree of just take order of n. So this is the best case for BST sort, and this is the worst case for BST sort, order of n square. So this is balanced BST, and for this time complexity is n log n. So now remember, worst case runtime for this sorting algorithm is order of n square, and the best case is order of n log n. So does it remembering us some sorting algorithm we know this performance? Yes, quick sort. So quick sort is having same type of behavior. Worst case it is order of n square, and the best case it is order of n log n. So why this is giving the same time complexity, that we want to see, because we will see the quick sort and this sort is having same number of comparisons in some order. So that is why they are giving same time. That observation we want to build now. So so to analyze that, we see that observation, the BST sort perform the same comparison as quick sort, but in different order. So to get that idea, let us apply quick sort on this input, which we have done for BST sort algorithm. So let us apply quick sort on this. So if we apply quick sort, suppose we have to choose a pivot and we can choose first element as a pivot. Now if we call the partition based on this pivot, what will partition does? It will divide this array into sub arrays. All the elements which are less than 3 will be in the left sub array, all the elements which are greater than 3 will be in the right sub array. Then again recursively we need to do the apply the quick sort like this. So let us continue. So this is the pivot. Now this 1, 2 is the element in the left sub array which are less than 3, and these are all elements in the right sub array which are greater than 3. Now again we have to call quick sort on this. Again we choose 3 as a 1 as a pivot. So again it will just put all the elements, there is none here in the left sub array, all the elements over which are greater than x in the right sub array. Similarly we will do it for this part. So 8 is the next pivot. So all the elements which are less than x will be here, all the elements which are greater than, so none is greater than 8, so all the elements will be in the left part. So again 6 we choose, so all the elements which are less than 6 will be here, all the elements which are greater than 6 will be here. So if you draw this tree, we will see this tree is same as the tree which we have built by build in a binary search tree build on this input. So that means what? That means they are doing same number of comparison, because here also 2 get compared with 3 and 1, and there also 2 got compared with 3 and 1. So that this is the observation. So that's why the BST sort is performing doing the same number of comparison as quick sort, maybe in some different order. Now here we are assuming one property of this partition algorithm. The property is, see, we know all the elements which are less than pivot will be here. So that is 1 and 2. But here we are assuming the order how they are coming in this input. So that is called stability. We remember stability? That is called stable sorting algorithm. So stable partition. That means 1, 2. If it is 2, 1, we may not get the same tree like BST, build BST. Similarly here, all the elements which are greater than 3 will be here. But in this order, 8 came before 6, 8 came before 6, like this. So this partition should be stable partition algorithm, and which is not hard to get, a stable partition algorithm. So that is the observation. So the expected, so now if we, the thing is, now if we just have a randomized version of this, both the sorting algorithm. So randomized version of the BST sort, what do we mean by that? We have given this input. So what we do, we just randomly permute that. Suppose this is our input, we have to sort it, we have to sort it using BST sort. What we do, before build BST, we just randomly permute this, and then we build BST, and we are interested to see what is the height of this tree, and we will see the expected height is log n. So that is means it is balanced. So in general, for any input, our BST is not balanced. If it is say sorted, we have a BST like this, we have seen, that is the worst case. But if we can do some random permutation on that, and then if we build the BST, then it is expected it will give a balanced tree. So that is the observation to bring. We had to compare this with the sorting algorithm quick sort. So that we will do. So the expected time to build the tree is asymptotically same as the running time of quick sort. So that is the observation. So that means the quick sort and the BST sort is having same runtime. So that means expected runtime of BST sort, randomized BST sort is same as expected runtime of randomized quick sort. So if you do that, this is the expected. So now what is the average node depth? Average node depth is 1 by n, and this is the time for build BST, summation of this comparison the sort. So that is basically depth of x. Now this is same as the expected runtime of the randomized version of the quick sort, and this is 1 by n because average node depth, and this is log n. So average depth node of a randomly built BST is log n, but that does not mean the height is log n, because we can take this example. If we have this tree here, only one branch is going little big, but here expected depth is log n, but the height is root over of n. So then how to prove that height is also expected height is log n for randomly bit BST. So for that we need to do some proof, and there we will use some probability theory. So this is the outline of this proof. We are not going to give the proof in this lecture. A little more maths is involved, probability theory is involved. So basically we will use this result, which is called Jensen inequality, which is for convex function. We have this property, expected f of expectation of a random variable is less than equal to expectation of f of x, and f is a convex function. And we will take, suppose xn is the height of a randomly built BST, then we take yn is equal to 2 to the power xn. And then if we can show expected value of yn, this we can show is order of n cube, and then we know 2 to the power expected value of yn is order of n cube, then we can take the log 3. So log then 3 will come out, this will be giving us log n. So that is the expected height of a randomly built BST is log n. That is what we are expecting. So that is the beauty. So this proof we are not discussing in this lecture. That is the beauty. So that means given any input, if you build the BST, so we may not get the balanced tree. We have seen that. If we have a sorted input, then it will be like this. If we have a reverse sorted, it will be like this. Height is n. But the magic is, if you do the random permutation on that input, if we then build the BST, then the expected it will be a balanced tree. So that is this theorem is telling. Okay. Now that is expected. Now my question is, why we are so much interested to have a balanced tree? What is the advantage of having balanced tree? The search query, because see, this is, say we have a huge data, we have some records, say student records, and each record is associated with many fields. Among these fields, one field is the, say, key field. So we have some records, say x is a record which is associated with many fields, or some, this is attributes. If you are familiar with database problem, these are the attributes. If a student record, one student has many fields, suppose roll number, name, CGPA, SGPA. Now depending on our application, we choose one field to be the key field. So this is key of x, depending on the application we are talking about. Say if we are interested to know the CGPA of a student, and if we want to search a student whose CGPA lies between this interval or maximum CGPA. So depending on the application, we choose one field to be key field, and based on this key field we will do all type of this operation like storing, searching, insert, delete. So we have n such records. This is one record, n such record, and from each record we get a n such key. So we have basically n numbers, and this number we store in a binary search tree binary search tree. Now how to search a record? Now suppose we have given a record, what we can do? We already form a BST, say. So we already form a BST. So this is the root, and then we have left child, right child, and so on. We have a tree over here, we have tree over here. So we store our database in a binary search tree way, and that we can do. We can just have build binary search tree. Now when you are searching a key, searching a record whose key value is something, what we do? We start with this node root, we compare with that. If that is okay, if that is the same as did, we got the key, happy. Otherwise we check the value. If the key value is less than, key value which you are searching is less than this root, then we have to go to the left subtree. And if the key value is greater than the root key value, we have to go to the right subtree, recursive call. So this way we continue. And then what is the search time? Search time is the basically height of the tree, how much height is the tree. So now if the height is balanced, then if there are n records, it is log n. So, search will be done in log n time. So, that is the thing we are, and this set is dynamic set, because we want to insert some record at any point of time, we want to delete some record. So, we want to make this set dynamic. So, basically we are interested in balanced binary search tree for doing this operation, insert, delete and search. Okay. Now, the tree we have seen by applying the random permutation, that is balanced expected, but the worst case it is like this. So, we want some guaranteed and no randomness, no random permutation. We want to have a guaranteed balanced binary search tree. So, that are that data structure we want to discuss now. So, there are few such balanced binary search tree in the literature. AVL tree, 2-3 tree, 2-3-4 tree, B tree, red black tree. So, these are all balanced binary search tree, guaranteed. I mean, we will see the data structure one of this, that is red black tree we will see in our lecture. We will discuss the tree red black tree, and we will see this is a balanced binary search tree. We will see the properties of red black tree, we will see the how we can insert a node in the red black tree, and this is balanced, guaranteed, no randomness, nothing, no expected height. It is a exact height, I mean height is log n. This is a balanced tree. So, now we will discuss the data structure red black tree, which is a balanced search tree. So, let us start the red black tree, which is a balanced binary search tree. So, it is a binary search tree, and we called this a binary search tree is a red black tree if it has these properties. So, first of all, it is a binary search tree, that means the every node, if you take a node in the tree, it will be greater than from its child as left subtree any node, and it is less than from the right subtree. That property is binary search tree. Along with that, if we have these 4 properties. So, and here every node has to be colored, and there are 2 colors, red or black. So, every node is colored either red or black. So, how to do that? How to implement that? A node can have a data point. We know a node contain a key and a pointer to the left child, right child, and we can have a pointer for the parent. And on top of that, to maintain the color, we can have a 1 bit of information. This is 0 or 1. 0 means red and 1 is black. So, any convention we can use. So, that can be easily trackable when we implement that. Okay. So, that is the every node has to be colored, and it is either a red color or black color. Now, the root node is black, and the leaves are basically our nils. We will see how the nils are coming. So, this root is black and the nils are also black, and this property is saying if a node is red, then the parent must be black. So, in this tree, if we have a red node, then the parent has to be black. So, that is one property, and this is another property. This is called black height property. So, given a node, every node, this is true for every node. So, we have this tree over here. Now, consider a node over here at any point, anywhere x. Now, consider from this node, consider all the paths, simple path from this node to the leaf. Simple path means we are not going this way, no cycle like this. So, direct path from this to the leaf. So, there could be many paths, this to the leaf. So, there are many paths over here. So, consider all the simple paths, and in this path there are nodes over here. So, we just count, we just see the color of these nodes. So, now we count the how many black nodes are there in each path, and that black node, number of black node on each path should be same. So, if this path is having 5 black node, this path also should have 5 black node. This part also will have 5 black node. This path will also have 5 black node. So, that is basically the black height of this node, and this 5 is excluding the color of this. This could be black, but we are not considering the color of this node. So, height means basically after excluding this node, this we do not count, if it could be black also. Height is 5 means in this path there are 5 black nodes. in this path there are 5 black nodes, in this path there are 5 black nodes, excluding this node, we are not counting this node in this black node counting. So, every path, every simple path from the node to its descendant leaves are having the same number of black node, and that number we called as black height of that node x. So, that is how that number is fixed, that is the property. If we having this property, then only we can say that is fixed, and that is basically the called black height of this node. So, that if these properties are satisfying by a red black tree, then it is called if these properties are satisfying by a binary search tree, then it is called a red black tree, and we will see why it is balanced. We will see the height of this tree, this data structure is log n, order of log n. Okay. So, that we will see. First let us take an example of a red black tree. Okay. First, this is suppose let us take this tree. This is a binary tree, binary search tree. You can check the property of binary search. You take any nodes here, say 18. Now, you consider all the nodes over here, which is in a left subtree. Their key values are less than 18, and all the nodes over here is key values are greater than 18. So, this is true for every node. So, this we can easily check, this is a binary search tree, and here you can see every node is colored by red or black. We colored the node. So, that can be handled by if we are using C language to implement struct node, we have a data field and we have pointer field, and we can have another field int color. So, we can have 0 for black and 1 for red. So, convention we have to fix. Okay. Anyway, that is that can be tackled by putting one extra bit of information in this node. So, now every node is colored, and now root is black. So, this is the root is black. So, that property is also satisfying, and these nodes are called new leaves, they are nils. Why we bring this node? Because we want to make it sort of every node should have the child, like this node have only one child, no left child. So, we want to make it complete in that sense. So, that is why we introduce the nils, new leaves, and these nils are, we will do it for all, because we do not know which nodes is having the one node or something like that. So, we do it for all the original leaf node, we will put the nils. If there is nobody, we just put 2 nils. If there is one node is there, we will put 1 nils. So, this way we will introduce the nils, and these nils are new leaves, and these nils are black. We colored these nils are black. Now, this height of this tree is 4, and this is, but we have to prove this in general. If there are n nodes, height is order of log n. So, big O of log n. So, that we will prove in a minute. So, before that we have to check the last property, which is called black height. So, let us consider the black height property. So, this is already we have seen, every node is red or black, roots and nils are black, and if a node is, so another property was, if a node is red, then its parents must be black. So, we consider all the red nodes, this is red node, parent is black, this is red node, parent is black, this is red node, parent is black. So, this has a significant, if you consider any path from root to the leaf, then in that path there must be more number of black node. So, black node is dominating, because from this property, because in that path if we have a red node, then we must have a black node parent. So, that means we cannot have more number of red nodes. So, that property will use, they help us to prove that this is a balanced tree. So, every node in this example, red node have a black parent. So, that property is also satisfying, and another property is black height. We consider any node. So, we can convention is black height of nils are 0, we can take. Now, we consider say this node 18. So, what is the black height? We take from 18 we take any leaves, a path to the leaf, simple path. This is one path. What is the number of black node? 1 and 2. So, this way we have 2. If we consider this way, it is 2. If we consider this way, it is 2. If we consider this way, all are 2. So, black height of this node is 2. Now, we check this node or this node. Now, this node is black, but we are not counting the color of this node in the black height of this node. So, we take path from this node to the leaf, this is black. So, 1, again this path 1, again this path 1. So, black height of this node is 1. Now, what is the black height of root? Root is black, but it does not matter whether we because in the black height we are not counting the color of this, but root has to be black, that is the one of the property. So, from root to the leaf we take this path, there are two black nodes, this 3 and nils. If we consider this path, say this path, there are this we are not counting 1 and 2 again. So, all the path you can check, there will be exactly 2 number of black node in the simple path from root to the any of the leaves. So, that is the black height of this node, and which is 2. So, we have checked the black height is also that property is also satisfying. Okay. Now, come to this this result, which is very important. That is why we are talking about this all these properties. I mean, our data structure should have these properties in order to have this data structure to be balanced, guaranteed. Okay. So, now this is the theorem we are going to prove. We are going to prove that if we have a n keys, n records or n keys, n elements, and these are stored in a red black tree, then the height of the red black tree is less than 2 log n plus 1. That means it is big O of log n. So, it is a height balanced tree. So, that we need to prove it. So, how to prove it? So, to prove it, we want to get rid of from this red node. We do not want any red node in the tree, but we cannot make it black. In that case, that property will be violating, that that black height will be violating. If we make this node to be black, then this way it is 2 black height, and this way it will be 3. So, black height will be, that 4th property will be violating. So, then the question is how we can remove these red nodes. Remove means how we can get rid of from the red node. So, idea is we know if a node is red, the parent is black. So, we can merge a node with the parents. That is the idea. So, that we are going to do. We just merge a red node with its parent, because we know if a node is red, then the parents must be black. So, that we are going to do. So, that means these two are, this node is red, but we know parent is black. This is also red, parent is black. So, we are going to merge these 3 nodes. So, this node, merging node, we will consider 3 data. So, that implementation we can easily take care. And this node is red, its parent is black, we will going to merge this node. This node is red, but parent is black. So, we are going to merge this node. So, if you do that, eventually we will be have this type of tree, this type of tree. So, we have here we have 2 nodes, here we have 3 nodes, here we have, and we have corresponding the leaves. So, these leaves are basically the original nils. So, number of leaves and number of nils are same. Okay. And this tree is called 2, 3, 4 tree, which is very nice tree, and it is uniform depth h prime of this. So, suppose h prime is the height of this tree, 2, 3, 4 tree. Now, we compare h prime with the original height of our original tree. So, suppose h is the height of this tree, which we are going to prove it is order of log n. Now, h prime is the height of this tree. Now, we have this relationship, h prime must be greater than equal to h by 2. Why it is true? Because h prime, if h prime is less than h by 2, in that case what we need? The h is the height means it is the maximum depth from the root to the leaf, maximum depth. So, we have a path from root to the leaf whose depth is h. Now, we know in every path we are only merging red node with the black node. Now, to be this less than, we need to merge more, like there should be more number of red node than black node, which is not possible, because we know if a node is black, red, then parent must be black. So, for every path from root to the leaf contain less number of, or maybe equal number of, contain less than equal to, less number of red node than black node, or maybe at most equal, that is why it is equality. So, h prime has to be greater than equal to h by 2. If it has to be less than, then we should have more red node in that path. That is not possible, because that will violate the property that node is red, its parent must be black. So, we have this property H prime is greater than H by 2. Now, we have we know this result number of, because here number of leaves are n plus 1, these are basically nils, we can easily verify that. And now leaves, here leaves are same, because these nils are basically blacks, which is we are not merging, we are only merging the red nodes. So, number of nils over here is same as number of nils. So, number of nils is also here in this tree is n plus 1. Now, let's look at this tree. In this tree, this is a 2, 3, 4 tree, means every node may have 2 child, 3 child or 4 child. So, that means number of leaves must be greater than equal to 2 to the power h prime height, because if we have every node is at least 2 child, so that means this has 2 child, say, so height is h prime, so it is 2, 2 square, 2 cube, 2 to the power h prime. So, minimum, that is the minimum number we are growing. So, at the last level, at the height, I mean height h prime level, we should have minimum n plus 1 elements will be there. So, n plus 1, the number of leaves must be greater than equal to 2 to the power h prime. Also, it must be less than equal to 4 to the power h prime, because every node can have maximum 4 child, but we do not need that inequality, we need this inequality. N plus 1 is number of leaves is greater than equal to 2 to the power h prime, because each node is must have at least 2 child. So, from here we can take this h prime is greater than equal to h by 2. So, or in other word, h by 2 is less than equal to 2 h prime. So, from there we can say that this is 2 to the power h prime. So, h prime is log less than log n plus 1, this is base 2, and log is monotonically increasing function. So, we can write that. So, basically h prime is less than equal to 2 log n plus 1. So, it is basically big theta of big O of, or big theta also big O of log n, because these are all this is constant, this is we can ignore. So, this is basically a big O of log n. So, this is a height is log n, I mean order of log n. So, this is a balanced binary search tree. So, for that we need to have those properties, all those 4 properties. So, we have proved that every red black tree is balanced. Good, that is a very good news. So, what is that has an advantage, because we are looking for balanced tree for what? For searching, for finding the minimum, for successor, predecessor, all this query, all this search query we can do in logarithm time, because we have to, for all this search query we have to go to the depth of the tree. So, that is height of the tree, and that is guaranteed log n. So, that is the time for all this query, search, finding mean, max, successor, predecessor. Okay. So, that is the beauty of this. Okay. Now, we will discuss how we can insert a node in the red black tree, because this set is dynamic, because this data structure we will use to store some records, and this set of records is dynamic. So, that dynamicness will be preserved if we can have these 2 operation on this set, on this red black tree, insert and delete. So, in this lecture we will just talk about insertion. Deletion is little tedious, which we will not cover in this lecture. So, for this both the operation we have to do this type of modification in the red black tree. So, operation itself, that means we have to insert a node in the red black tree for insert, and we may have to change the color for the nodes to make it again red black tree. And then maybe only changing color will not help us to get back the red black tree. We may have to do some restructuring in the tree. So, that is called rotation operation. So, that also you have to see. Only color change may not help us, only color change may not get back to a red black tree again. We have to do this restructuring operation, that is rotation, that we will discuss. So, let us take this what type of restructuring rotation property, rotation operation we can do. So, suppose this is a part of the tree, we have tree on the top. So, this is a node B node, this is a node A, and these are the subtrees rooted here. So, this is left subtree of A, this is right subtree of A, and this is the right subtree of A, and this is the left subtree of B. Sorry, this is the right subtree of B, and this is the left subtree of B. Now, we want to make A up, B down. So, that will be done by rotation operation. So, that is called right rotate A. So, we want to make A up, B down. Now, this is a red black tree. So, that means all the nodes over here, I mean having all the properties, and moreover this is a binary search tree. So, that means value of alpha is less than, so any key values over here is less than the key value of A, or any key value over here is greater than key value of A, and any key value in this part is less than key value of B, and any key value in this gamma is greater than. So, that property we should have. Okay. And also these are colored basically. So, now this rotation how we will do? We will just make A up, B down. So, that means this tree will be hanging with A as it was, and the beta, the right subtree of A will go to the left subtree of B, and the parent of B was somebody else over here. Now, parent of B will be A, and right subtree of A was this this beta hanging tree, and now it will be the node B, and these two are hanging with the B node. And you can easily verify these properties are satisfying, this binary search tree properties are satisfying. And here, so how much time it will take to do that? This is called right rotate operation on A. We want to make A up, B down. So, it is just changing few pointers, because the parent pointer of B was somebody else, now it is A, and the parent pointer of this node, the root of the beta was A, now it is B, like that. So, just we are changing 3-4 pointers. So, it is a constant time. Okay. Now, if we have given this node, given this structure, from this structure we want to get back this structure. That is also one operation, that is also rotation. We want to make A down, B up. This situation may occur, we will see that. So, that will be done by this left rotate B. So, that operation is called left rotate B, and all the operation will take, and this we can check, it is preserving the binary search tree property, and all the operation will take constant time, because it is just changing few pointers, and maybe you can use the color also, reload the color, that we will see later stage. Okay. So, these are the rotation operation we need to use to for the insertion or deletion. Okay. Now, let us talk about quickly insertion algorithm for red black tree. So, we have given a red black tree that is already a balanced tree. Now, suppose, and this data structure is dynamic. Now, suppose we want to insert a node X in the tree. Now, given a tree, if we insert a node, it will be binary search tree insert. So, we compare with this root. If the value is less than, we go to left part. If the value is greater than, we go to right part, like this, and then we keep on going. This is a recursive call until we reach to a leaf node, and once we reach to a leaf node, we insert that node, and we have the new Niels, all these things. Okay. So, now that will be taken care by the binary search tree insert. Now, we need to color this node. Now, which color we will use to give this node? So, idea is, if we should not use the black color, because if we use the black color, then there is a chance that it will violate the black height property, the property number 4. So, that is the danger. So, only thing we can, to be safe side, we can give the color to be red. So, then also suppose we give the color of that new inserted node to be red. Now, if the parent is black, we are lucky, we do not need to do anything, but problem is if the parent is red. So, we have already inserted node X and we make the color to be red in order to avoid the black height property violation. We make it red. Now, fine. Now, if the parent of that node is black, we are safe. but if the parent is the parent of that node is red, then we have a problem. So, that is the thing we need to fix. So, that violation is there, and that will be we will discuss by an example. Suppose this is the given tree, we have already have this tree, this is a red black tree, we just have seen this. Now, suppose we want to insert a node over here. Suppose we are inserting record whose key value is 15. So, how to insert? BST insert, binary search tree insert, we compare with 7, then 15 is greater than. So, we call this binary search tree insert on this node, on this subtree, recursive call. Again 15 is less than this, we go for this subtree, again 15 is greater than this, we go for this subtree. This will continue until we reach to a nil. Again we call this insert on this subtree, we will go here, and then here there was a nil lib node. So, we got a nil, we will insert 15 over here and we will make new nils, and we put this color to be red. Now, if this was black, we are okay, but this is a problem. Now, this is a black node whose parent is also black, sorry, this is a red node and whose parent is also red. So, we have a difficulty over here. So, now first we will try to recolor it, and we want to see whether by only recoloring we can manage this. So, that way we will see, suppose this, so how to recolor it? So, it was this two node was red, okay. So, we make it black and we make this to be red. So, that means so this is parent, this is the GAN parent, and this is the so this is parent and this is auntie or uncle. So, this is one case, one situation where a node is red whose parent is red and uncle or auntie is red and the grandparent is black. Then we will try this, we will make this to black and this we make it red, and that means we propagate this to here. Now, here we have a problem again. If it is black, then we are done, but this is not a black node, this is a red node, we have a problem here. This problem we move it to here. So, now here this is parent, this is uncle, these two are not same color. So, we cannot apply the case 1. So, we have to apply something called case 2. So, that we will see. So, in that case we have to rotate, we have to use the all the color changing will not help us, we have to rotate. We do the right rotate of 10. So, we make this 10 up, 18 down. So, we will do that. So, for that right rotate, if you remember, this is A, this is B, we want to make A up. So, this is our alpha, this is beta, this is gamma. So, this by that right rotate, if you recall. So, this parent of 18 will be this and alpha will be hanging here. So, beta will be hanging to the left part of this like this. So, we do that. So, this is the structure. Now, after this again we have to write. So, this is case 2, this rotation what we did. Now, if we have to do the case 2, we have to go for case 3. So, case 3 is this one, we do the left rotate of 7, we make 7 down and 10 up. So, that is we know. So, we do that. So, alpha, beta, gamma, again we need to arrange this same way, and then we go for the recoloring of this node to make it again the red black tree. So, that try we will do. So, what is the and then finally, this is the red black tree. Okay. So, what is the so this is the code. So, this is the code pseudocode, we can quickly go through it. We want to insert a node X in a red black tree, we will just do the BST insert and then we make the color to be red. Now, if this is case 1, if the uncle or aunt, if the color of the parent is black, we do not need to do anything. If the color is red, then we have to do something. This is what is referred as case 1. We change the color of this 2 node and color of the that parent, I mean grandparent. Then, if it is still the that grandparent is red, then we have to do case 2 followed by case 3. Now, what is the time complexity of this? So, this is the graphical notation of this, we are just skipping this. Okay. So, we are just this is the case 2 and if we have to do the case 2, we are going back to the case 3. So, yeah, so this is the analysis. So, what is the time complexity of this? So, time complexity will be, because the rotation will cost us constant time, but we may have to go rotating up to the from lip to the root kind of height of that. So, run time of the insert will take order of n times. So, that is also okay. And deletion we did not do in this lecture, but deletion also can be taken care by this order of. For that we need to know the deletion of a binary search tree deletion. For that we need to find the predecessor, successor. So, all this operation we need to discuss. So, let us conclude the talk. So, we have in this lecture we have discussed balanced binary search tree. So, what is the importance of balanced binary search tree? If we can store our record in a balanced binary search tree, height balance, then we can guarantee that the search can be taken, search can be done in the theta of n times, log n times. If there are n nodes, we can do the searching in log n time, which is very fast. Say for example, if we have 2 to the power 100 nodes, and then to search it, if you have to do the linear search 2 to the power 100 seconds, say, it is huge. It is not possible in a lifetime. But if we can store our record in this balanced binary search tree or red black tree, then we can do the searching in log n time. Log n means 2 to the power 100 log that base 2. So, it is just 100. So, which is very less. So, that is the importance of this. So, thank you very much.